Everyone, welcome to this session on design patterns designed specifically for project managers and development teams. This is part of our technology project manager series where I'm trying to break down the technical concepts for especially non-technical managers managing technical teams. We'll cover fundamental design patterns and some architectural principles. By the end of the session, you'll understand not just what patterns are, but also why they matter and how they help us to build scalable and maintainable systems. With that context, let's get started with this first question. So, what are design patterns? Design patterns are reusable solutions. Design patterns are reusable solutions to recurring software design problems. Think of them like architectural blueprint for buildings. Architects don't reinvent the walls or doors every time they design. They just reuse proven patterns, adapt to context. Similarly, developers reuse the coding patterns, and that is what these design patterns are about. They improve reusability, solving problems once, then applying the solution in many different places where a similar problem exists. Maintainability, making it easier to evolve systems without breaking everything. Communication, giving teams a shared vocabulary. For example, instead of explaining a class that notifies others when it changes, we just say observe a pattern. So, patterns are language of proven design wisdom over time. Let's move on. So, where did all this start? What are the origins and evolution of design patterns? So, patterns started outside software. In 1977, Christopher Alexander used them in architecture to describe recurring building solutions. In 1980s, Kent Beck and Ward Cunningham saw their potential in programming. And in 1994, the famous Gang of Four, Gamma, Helm, Johnson, and Lecitis published Design Patterns, the elements of reusable object-oriented software. It's a book which cataloged 23 patterns which are still widely used today. Over time, patterns expanded beyond objects into enterprise architecture, concurrency, and microservices. Just as Agile shifted software from rigid planning to iterative improvement, design patterns shifted the focus from ad hoc problem solving to systemic design thinking. Let us look at the different categories of design patterns. Primarily, they fall into four categories. Creational, how objects are created, like example is factory method. Structural, how classes and objects are organized. Behavioral, how objects interact. Concurrency, how we handle multi-threading and parallelism. Each category addresses a specific different dimension of software complexity, like creation, structure, communication, or performance. Let's deep dive into each of these different types of design patterns, starting with creational patterns. Creational patterns abstract the process of creating objects. Examples: factory method used in frameworks where the type isn't known upfront. Imagine a UI framework creating different button types depending on the platform, like Windows or Mac, web. Singleton ensures only one instance, like a configuration manager, but beware, it can make testing harder. Builder pattern, step-by-step construction. Think of building a SQL query with optional filters like where, order by, or limit, without writing messy constructors. If your team is repeatedly hard coding constructors or duplicating setup logic, it's time to introduce a creational pattern. Structural patterns. These show us how to combine parts into larger systems. Some of the examples are adapter. Think of a payment gateway integration. Stripe or PayPal have different APIs. An adapter standardizes them so that your app doesn't need to change if your service providers have to be changed. Decorator. Imagine adding encryption or logging to data streams. Instead of rewriting the class, you wrap it dynamically. Facade reduces complexity. An API gateway is a real world facade. It hides multiple microservices behind one clean endpoint. Composite used in a tree like structure such as file explorers, menus, or org charts. A folder and a file can both be treated the same way. Structural patterns help teams design flexible, modular systems where change in one part doesn't ripple everywhere. Next is behavioral patterns. Behavioral patterns handle communication and responsibility. Observer, used in event driven design. When stock price changes, all subscribed apps get notified. Strategy, choosing algorithms dynamically. For example, applying different tax rules in different countries without rewriting the core logic. Command, used in undo, redo, or task queries. Each user action is packaged as a command object. Others like state, chain of responsibility, and temple method are essential when workflows grow complex. Agile teams often struggle with feature toggles and business rules. Behavioral patterns provide cleaner ways to manage that complexity. Next is concurrency and architectural patterns. Most applications must scale across multiple threads and cores. Concurrency pattern include producer, consumer, background jobs processing tasks from a queue, thread pool, web servers handling thousands of requests efficiently, actor model, popular in systems like Akka or Erlang, where isolated actors communicate through messages. Lock free patterns, high performance systems that avoid deadlocks. Next, let's look at some architectural patterns. At a higher level, architectural patterns shape entire application. Microservices, which are independent, scalable services, great for large enterprises. Monolithic, everything in one unit, good for small teams which are starting out. Layered or entire, separation of UI, business logic, and data. Event driven, services communicate through events used in modern e-commerce and IoT. Concurrency systems make systems faster, while architecture patterns make them sustainable in the long run. Solid principles are the compass for object-oriented design. Single repository, one reason to change. Open, closed, extend, don't modify. Liskov substitution, subclasses should work anywhere the parent works. Interface segregation, don't force clients to use things they don't need. Dependency inversion, depend on abstractions, not implementations. Also, we need to be watchful of some of the anti-patterns, which are common responses to recurring problems that are ineffective or counterproductive, often lead to negative consequences, increased technical debt, and reduced maintainability. Beware of these anti-patterns. Some of these are like God object, a class that knows everything. Spaghetti code, tangled unstructured piece of code. Golden hammer, using your favorite design pattern everywhere. Premature optimization, fixing performance before identifying the real bottlenecks. Vendor lock-in, becoming dependent on single one provider of your infra or tool or whatever. Follow solid but clean design. Avoid anti-patterns to prevent technical debt. Let's conclude with the role of a technical project manager. Your role is not just coordination, but a facilitator of design excellence. That means assessing current architecture for improved opportunities. You keep assessing the current state, running workshops or code reviews to educate teams, setting standards and guidelines for consistent practices, enabling collaboration across teams when architectural trade-offs arise, monitoring technical debt, and ensuring business context drives design choices. The best pattern isn't the most sophisticated one, but it's the simplest one that solves the problem effectively. That wraps up the design patterns short session. We covered what patterns are, where they came from, their categories, practical examples, architecture implications, and a technical project manager's role. If you found this useful, make sure to like, share, and subscribe to our channel. Thank you for watching.